Okay, can everybody see this and can everybody hear me okay?
Yes, sir.
Good. Okay. So I'm Elliot Eichen, and I wanted to run through a little bit about what type of research is done inside the wireless interdisciplinary research group in the computer science department at University of Colorado Boulder. And hopefully this will take about a half hour. Please feel free to ask questions. Um, in the middle or in the end, whatever works for you. And I'll start if nobody has any problems. So here's kind of what I wanted to cover. First of all, the recent work inside the group has been in spectrum engineering and spectrum management. And that has, in turn, has two big areas of concentration. One has to do with protecting radio astronomy observatories from radio frequency interference, and the other is protecting weather and climate remote sensing satellites from interference created by terrestrial 5G and 6G networks. And you guys can read this as well as I can. And then the other pieces that have gone on in the last 2 or 3 years have to do with the lunar communication systems, radio frequency noise sensors for various applications, including CBRS, and qubit resistant cybersecurity. My interests have been in the interference between 5G and 6G networks and really important climate remote sensing satellites and qubit resistant security. And I'm going to focus today on the spectrum sharing work. What I hope that you get out of this is some sense of what the actual research is and how it works, as well as a sense of what's the set of skills that would be needed in order to do this research and what the expectations would be for doing this research, and then some personal observations on how to be a successful graduate student from someone who has a lot of scar tissue having to do with both being a graduate student himself a long time ago and watching graduate students over many years. Okay, so quickly, this is me. I grew up in New York City and I have a PhD in a BS in physics and a PhD in optics. Um, Most of my career spent in the telephone research labs back when we actually had telephone research labs and they were really quite good, Bell Labs and GTE Labs. And I retired in 1917. In 2018 and 2019, I was an IEEE Congressional Fellow. It was sort of my penance for working for so long for the telephone companies. And I worked for Ron Wyden and I supported the Senate Commerce and House Science Committees. Um, and that's basically me. And you can read this as well as I can read this. And I've been at the University of Colorado now for about a year. Okay, so I want to talk about spectrum management a bit. And it's not a particularly sexy sounding topic, but it's an extremely important topic. So if you look at Wikipedia, the source of all knowledge, they say it's the process of regulating the use of radio frequencies to promote the efficient use of the spectrum and the gain a social benefit. Effectively, spectrum is a scarce research, and there's been such an enormous demand for wireless services over the last couple of years that it places enormous stress on the amount of spectrum that is out there. In some sense, you can think about it a lot like water. There's a limited source of water, and the more applications and the more people there are, the more stress there is for clean water. And the same thing is true for spectrum. and it's really important. Okay, if you look at the spectrum is electromagnetic radiation. What we think about spectrum, goes from someplace down here, which is AM radio, all the way up to 6G communications at something like 3 or 4 terahertz. So that's 5 orders of magnitude in terms of the frequency or the wavelength of the light. Okay. Um, so this is a field that is primarily either in computer science departments or electrical engineering departments, but it's very interdisciplinary, right? It really requires expertise from many different places. As I said, it's not nearly as sexy as the hot topic du jour.
Recording in progress.
Can you still hear me?
Yes, sir. Yes, sir.
Okay, so it's not nearly as sexy as machine learning or cybersecurity, but it's really important. And once you get into it, you'd find that probably that it's pretty interesting, because it's so interdisciplinary. It takes people who are with expertise in computer science, electrical engineering. There's this whole aspect of how technology or science informs policy, and there's also economics. And the other really interesting thing about this is that there are lots of jobs, and there are not many folks available to fill them at this point. And there will be jobs for a long time. This is another way to look at spectrum. So if you look at spectrum in the sense of going from AM radio to 6G communications, that gets divvied up in the United States by the FCC and the NTIA. And this is the table of frequency allocations. And, obviously this is an ICE chart, and I'm not, looking at you to actually be able to see it, but it gives you a sense of how complicated this is and how many applications there are for this stuff. And it becomes very contentious because all of these applications have embedded users and with applications, and all of a sudden you're trying to squeeze more and more and more use out of this box, which is a finite size. And that's what this is all about. This is all about protecting really important applications that use this spectrum while making more spectrum available for more applications. Again, if you guys have any questions, let me know. Okay. So in particular, the thing that I'm interested in is the interference between passive microwave remote sensing and 5G networks. Okay, so the legacy users for the gigahertz band, one of them are satellites that are used to measure water vapor in the atmosphere. And those measurements are really important for both predicting the weather. They're also really important for climate models. And that's how I got interested in the subject. I got interested in this, I had spent a year on the Hill working for Ron Wyden, and I went to the Congress because I was interested in quantum computing. Nobody in the Congress was actually interested in it. Everybody knew it was important, and so there was no debate about it. It was being funded. But this was something that was very strongly debated. The FCC was trying very hard to allocate these frequencies to benefit the wireless industry. And the NTIA was trying very hard to protect the legacy users, the Department of Defense, NASA, and NOAA, and radio astronomy folks, because their use of this spectrum was really important. So NOAA uses this spectrum they measure water vapor in the air column from a satellite that is in polar orbit. And they do it at many different frequencies, all in the gigahertz between about 20 gigahertz, actually between 5 gigahertz and 100 gigahertz. And by looking at all of that, they can get the temperature gradient through a column that goes all the way down into the atmosphere, as well as the amount of water vapor. And water vapor is the engine that creates the climate, that creates this removes heat from the surface of the Earth, okay, and puts it up into the atmosphere and hopefully re-radiates that energy back into space, okay? And the problem with it is that you cannot distinguish between, if you're measuring these quantities with these very sensitive radiometers, and I'll go into that a little bit, you can't distinguish between, is the radiance that you measure due to transmissions in the red line, which would be the power spectral density of a wireless communication system, or is it due to vibrations of the water vapor molecules? And as I said, again, I got interested in this because I was very interested in climate and climate modeling. Okay, so how does this actually work, or what's going on here? Well, these satellites are called Earth exploration satellites, and they measure the radio frequency from rotational transitions of water vapor molecules between, let's say, 10 and 20 gigahertz. The sounders are basically the receivers of a radar, but they're extraordinarily sensitive. One way to think about them is that people sometimes say that if you turn on a light bulb and point it up at the sky, these radiometers will see the radiance, the light from that light bulb, the equivalent in the gigahertz spectrum. They measure average power and have very long integration times. And they're extraordinarily sensitive compared with the receivers that go into a mobile phone, and compared to the power that gets generated by a mobile base station. There's something like 10 to the fourth or 10 to the fifth times more sensitive than the communication receivers. And these communication receivers are already amazingly sensitive. And you can't distinguish because the integration time is so long, it's in the milliseconds, and because the communication signal is changing so quickly, on the order of tenths of microseconds, you can't distinguish that it's a communication signal. All you're doing is measuring the average power. And because of that, it becomes very, very difficult to distinguish these, the amount of power that you collect. Is it due to the water vapor molecules, or is it due to some form of 5G or 6G transmission? So why are the measurements important? Well, I don't need to go into that, I hope. Weather forecasting sounds like a boring thing, but if you think about it, knowing when and where there's going to be hurricanes or tornadoes or snow or drought, and the implication that has on, crops, the implication that has on aircraft, on ships, just everything in your ordinary day-to-day existence is extremely important when it comes to human life. So that's one reason why they're so important. And then another reason why it's so important is that climate models are extremely important. The climate is such a complicated and dynamic system, that there's always this discussion of, the butterfly, flaps its wings in someplace, in South America, and 100 years later you get a tornado someplace, in the United States, or snowfall in Europe, something like that. And that's, due to the complication, the complex nature of the system. Okay, and being able to predict climate is extremely important, as you well know. So this work is part of a common theme that the group has, which is called real-time geofencing. So, as I alluded to, some of the work of the group has to do with protecting radio astronomy from satellites that are transmitting down to the Earth. Okay, so if those satellites up in the Earth can be satellites, or they can be communication satellites, they can be communication constellation satellites, such as Starlink, or they can be other types of satellites that are just sending data up, back and forth between the ground and the Earth. And it's kind of the same thing. These radio astronomy receivers, these dishes, are immensely sensitive because they're looking at the radiance produced by stars and galaxies, millions of light years away. And so if a Starlink satellite flies in the path of the radio receiver, all it sees is Starlink. It doesn't see light from any of the objects in the universe. So the opposite phenomena to this is the work that I'm involved with. Instead of having a receiver on the ground, you have a receiver in space up here, a satellite with an antenna. And that antenna is going around, let's say, in a circle as the satellite moves across the face of the Earth. And as soon as the field of view of the satellite subtends the pixel, the measurement pixel of a 5G or a 6G transmitter, the radiance from that 5G or 6G transmitter is enough to drown out the natural radiance of water vapor close to the Earth's surface. So that is the work that we're doing, and we do it. There are lots of, different ways to think about spectrum sharing. You can do time-dependent spectrum sharing. You can do space-dependent spectrum sharing. You can do a combination of both of those things. In this case, we're doing spectrum sharing or geofencing, sharing by geofencing, by somehow changing or moderating the power that comes from a transmitter here. And you can do that by changing the amount of power that's emitted. You can turn off the transmitters. You can move them to a different band, one in which the satellite is not sensitive to. So this is work that's been going on in the group probably for about 4 years, something like 4 or 5 years. We've had a number of salient support from the National Science Foundation, culminating with the most recent grant from the National Science Foundation for protecting radio astronomy observations and Earth exploration satellites. This just gives you a sense of how this stuff works. This is probably the most sensitive and most advanced radiometer. This is a 5G. This is a something called ATMS. There are, I think, 3 or 4 of these now. Each one of these satellites costs billions of dollars. This is what's called a cross-track scanner. So if the satellite is going in this direction down or in this direction up, the scanning mechanism is going 90 degrees from that, back and forth. So that's called a cross-track scanner. And each one of these is a pixel, is a measurement. So you have to predict very precisely where that pixel is going to be at a certain point in time. And if you can do that, then you can modify the 5G network so that it doesn't interfere with the satellite measurements. And here's just another way. This is how you geofence. You can think of a single pixel, which is the red circle here, oval here, and here is sort of a bounding box around that pixel. And it's, about a pixel wide and so it's a pixel on top, a pixel on the bottom, and then a pixel to the left and the pixel to the right. So that forms the bounding box, and that is the way that you would geofence this kind of stuff. I'm going pretty quickly. Are there any questions so far? This making sense? I see one hand. Go ahead, just talk.
Hello, Dr. Elliot. My name is PSA, and I have a question on 6G, the 6G and beyond communication. So
Okay.
Hello, please, am I audible?
Yeah, go ahead.
Yeah, so in 6G and beyond, terahertz and sub-terahertz frequency bands will mostly be used. And my question is, can the current antennas we have, or the current wireless radio support these bands, or there'll be a need for a total redesign of antennas to support these bands, the terahertz and sub-terahertz band?
So for certainly the antenna structure for 5G, we have phones today that support them. These antennas are pretty different they're much smaller because obviously the wavelength is smaller, the frequency is much higher. Most of the 6G work that I'm aware of tries to exploit frequency bands that are over 100 gigahertz. And again, that's part of you continue to shrink the size of the antennas, and you have to increase the sensitivity. But the other side of that equation is that because the antennas are smaller, then you can have many more antennas for a mobile device, and that allows you to use more MIMO capability as a way to address the devices to provide spatial diversity. So I think that work is going on. I don't think that that's a killer at this point. We know how to make pretty good antennas at in the gigahertz range, and making more antennas that are smaller. You're still not close to the tolerances of that you need when you make integrated circuits. Did that help?
Okay, fine. Thank you.
Sure, it's a good question. Okay, so as I said, this is an example of what a single pixel would look like. So where's the work at this point? So after these multiple grants from the National Science Foundation, we're basically closing in on the completion of a proof of concept system. And I don't know if you can see the system here, but basically this is a front end to the system where you provide the latitude and longitude of the base station, where it is, the date for it, what the frequencies are that you're interested in, and if you pick a particular satellite, it'll provide a response that tells you down here in red the times that you might have to modify that satellite. Now, this is for human consumption, right? What you have really when you want to use this is you have a machine-to-machine interface that is providing that data to millions of G-node Bs, and each one is getting its own feed for when it has to turn itself off and turn itself on. And this work will run through the September of next year. So in the United States, this type of work will feed into something that's called the National Spectrum Strategy. So the US has a plan in terms of how to how to get the most bang out of the amount of spectrum that we have today, right? So as I said, we have a limited amount of spectrum. It's not going to get any bigger, really. So how do you use it more efficiently? And this is an extremely important worldwide problem, and one that has to be addressed. And the U.S. has a large, what's the right word, strategic plan for how this is going to work. So all of the large vendors, Qualcomm and Intel, and all of the carriers in the US as well as in the world can feed information into that because they're one of the users. The other set of users are governments that use spectrum for Earth sensing, for science reasons, for national defense. And they have different ways of inputting their concerns and their use of spectrum, and that will get monged up by the government. And in 2 years, there will be a plan, supposedly, on how we go ahead to divvy up the spectrum and still make more of it available for the wireless communication users. Let me see if there's more questions in the chat. Okay. Nope, no more questions in the chat. So the work that we're doing will go from this work, proof of concept, really into a prototype deployment. And the deployment that we are targeting is one at 7 gigahertz, something called sea surface temperatures, because these measurements are particularly important for determining where hurricanes will land, where they'll make land, and when they'll make land, and how much water will be dumped, or what's the precipitation probability. And so this is a low-hanging fruit. This was a particularly easy set of satellites to geofence and a particularly important subject. And the 7 gigahertz band is a really important band because it is in this sort of sweet spot where the wireless carriers can deploy this type of transmitter inside their existing footprint, their existing antennas. So that's one of the places where this work will go. And then the other place where this work will go has to do with verification of geofencing at the pixel level. And I haven't gone into this in great detail, but these pixels exist for milliseconds, right? And being able to geofence at the millisecond level allows you to keep the network availability of a 5G network high. And so you want to be able to geofence at the pixel level. In this case, we can geofence at a scan line level, so it's much more forgiving. So this is an easy one to do, but eventually this will become an important thing to do. So go ahead, please talk. Go ahead.
Hello. So I want to ask about the frequency band, the 7.4 gigahertz. So has it been allocated to UC Boulder or is being shared with another organization? The 7.4 gigahertz for the prototype.
Go ahead. What is the question? I'm sorry, I missed what the question was.
Okay, so let me come again. Okay, so I wanted to ask about the frequency band 7.5 gigahertz on the previous slide. So has it been allocated for UC Boulder for this kind of testing or prototype, or it's an available frequency band for use by other organizations too as well?
Right. So this band here, it's 250 megahertz. So it's 150 megahertz, 125 megahertz on either side of 7.4 gigahertz. And it's currently being used to measure sea surface temperatures. It's actually a complicated measurement. You use 6.9 gigahertz and 7.4 gigahertz, and you combine the data from those, and you're able to extract out the surface temperature of the sea in coastal regions or in the middle of the ocean. So that's the current use of that. And what the US is proposing, and this is also something that is going to what's called the ITU, the International Forum from this, is to use a lot of this band for wireless communications because it's relatively low frequency. Did that
Okay.
answer your question?
Yeah, thank you. All right, yes.
Okay. So there's a lot of stuff all at once, hard to sort of distill it inside a half hour. But at this point, you may be wondering, where's the computer science in all of this stuff? Because, I've been talking a lot about what seems to be physics-y or electrical engineering-y, but there's an enormous amount of computer science in here as well. Okay, so you've probably heard about digital twin models. And in this case, we need a digital twin to tell us how much power we need to reduce, or what is the impact of the transmissions in these places. And that modeling is both causal as well as stochastic in nature. And that in and of itself is an interesting problem. In order to prototype, to actually build this stuff and to make it work across hundreds of thousands of base stations and endpoints is a very complicated systems development problem. So I didn't talk about the architecture. I have a couple of slides following this. But basically, the implementation of this stuff is done using what's called a spectrum access system or a zone management system. And these are complicated pieces that sit generally outside of the network management systems of the telcos, of the wireless service providers, and they talk to the network management interfaces of these wireless communication systems. And those interfaces then in turn go ahead and they talk to the individual base stations. And it's complicated. I mean, it's just, it's enormously complicated. And so the systems architecture and the development and the testing of all of this stuff takes lots of people, and you need to do it efficiently and in a reasonable way. There are also lots of security implications, cybersecurity, national security, that relate to this stuff. So the location of all these base stations, in some sense, can be thought of as a national security issue or a local issue, as well as the information that passes across all of these networks. So part of the system architecture has to do with cybersecurity. A lot of times you're making very fast decisions based on incomplete information. And so machine learning algorithms become very important in building these spectrum access systems. Another thing I haven't really talked about, but all of these systems have policy implications. So the way this works across the world is every 4 years, the International Telecommunications Union, which is a part of the United Nations, gets together and they vote basically on what bands to use, what bands not to use, how much protection you need to provide, things like that. And so not only does the digital twin, does the modeling feed that type of before it actually gets to deployment, but there's lots of things that have to do with how you generate requirements that in fact fit into that policy. And there's a whole field in computer science that has to call formal methods that basically say, did I tell you enough so that you can build requirements that are neither over constrained or under constrained? And there's probably a lot more computer science in this than I've talked about. So let's see, how am I doing on time? Not great. So I have a couple of slides just to sort of show you what the architecture of these things look like. I think it's enough to say that they're complicated. There's lots of modules, lots of pieces, lots of moving parts that are important. And each one of these little boxes contains many other little boxes. And so this requires a knowledge of you require computer science knowledge in order to how to build the systems and how to architect the systems. You need to have domain knowledge about how they work, how the 5G networks work, or the 6G networks work, or how the communication satellites work, or the weather satellites work, things like that. And the other thing is that this is a commercial system. So there is one example of this type of dynamic spectrum sharing that's available today. It's called CBRS, the Citizens Band Radio Service, and it doesn't protect against weather satellites or radio astronomy, but what it does is it allows a certain amount of spectrum to be shared with radar systems, which are generally coastal systems. This is an example of one of the spectrum access systems that makes that work. This is an existing service, an existing band. This is at 3.5 gigahertz today. This is Google's implementation, but there are a number of SaaS providers that have operating SaaSes that the networks depend on in order to make this work. And this is yet another block diagram of how this might work for geofencing low Earth orbit satellites. Publications obviously important. I just when I put this talk together this afternoon, I realized that none of our 2024 publications were there, which is a miss on our part. So we better catch up on that. It's important to publish because it's important to let people know what you're doing. And this is a worldwide problem, a worldwide issue, and what's nice about being in academia is that you have peers and colleagues all over the world. And this is one way you work. Please go ask your question.
Hi, Professor. I just wanted to know that are these spectrum can be shared by different operators? Because I am a telecom engineer working in Bangladesh. In my experience, I have seen that different operators, they use different spectrums. They cannot share spectrums. Can we use spectrum sharing in between operators in future?
So the answer is yes. That's another can of worms. That is another topical area. But yes, you can use, there are different ways to share spectrum among operators. So in this case, we are sharing spectrum between the service provider and another user of spectrum, but there's a similar field might be how to share spectrum among multiple service providers. And I'll give you a quick example of that. So let's say there is Spectrum X, which has 1,000 satellites in orbit around the Earth. And let's say there's also Elliott-Eichen spectrum service, and I'm going to launch my set of satellites, and I want to use my set of satellites in the same spectrum as Spectrum X. Well, how do I do that? There are different ways to do that, but one interesting thing to think about there is that you can time-dependently share the spectrum, but you can also multiplex the spectrum by angle. So a combination of some form of it's like MIMO, but it's not really MIMO, but some sort of angular dependent spectrum as well as time dependent spectrum sharing in order to do that. And there's been a lot of work on the time dependent stuff ways, so that you might think of having a national user like the Indian PTT would own the spectrum and would allow different service providers potentially in real time, almost like an 802.11 protocol to share spectrum. So the answer is yes, but that's not specific to this work, but it's in the spectrum sharing arena.
Okay, thank you. Thank you.
Sure. So another really important thing, if you back out a little bit and you start looking down at this stuff, is how do things get done as in science and technology? And one way they do it is by collaboration. These problems are so complicated and they touch so many different entities that you need a large team. And you need a large team not only at the university, but you need colleagues all over the world. And so the colleagues that we work with, in particular for this set of work, we work with people at BU, we work with a group at UC Berkeley, we work with collaborators that are in industry. We work with NOAA, which is the National Oceanographic and Atmospheric Administration in the United States. This is the people that create the satellites, build the satellites, and also forecast the weather. And in our case, from a policy perspective, we also brief people in the US Congress. And we work with the University of Utah and lots of different collaborators. So without going through this in great detail, it's really important to collaborate. I thought it might be interesting to give you also my perspective on what is needed to be a student and work in some of these areas. What would we expect a student to come to us with in order to be able to play in this sandbox? We would expect the student to be able to code pretty well, to have a pretty decent idea of the standard things that you need in order to code. You need to be able to use a version management system like Git. You need to be able, our code is generally written in Python, but all the languages are pretty much the same. And what I really look for in a large test is somebody who can think, right? You have to be smart enough to and dogged enough to be able to solve problems. At the master's level, the MS level, that is pretty much what we would be looking for coming into the program and coming into the lab. What we hope that you get out of it, going out, is some domain experience in at least one of the many areas that are partial to this. So not only do you know about how to code, but you may have brought something back that has to do with machine learning or system architecture or, time-dependent spectrum sharing. We expect that, you would be able to not necessarily be an expert, but that you would have a strong familiarity. We also hope that you will gain presentation skills. We think it's very important to be able to communicate and collaborate. So we would expect people to have gone to a large, science conference or an engineering conference and be able to present some of this work. So we would expect you to do that. Maybe you would be the co-author on a paper, maybe not necessarily the first author at the master's level, but you could be a the main author as well, and that's happened before. Typically, this takes 1 or 2 years to do. Well, I called it indentured servitude. I hope you understand that that's supposed to be funny, a joke. It's not indentured servitude. In fact, being a graduate student is a wonderful time in your life. Very few other times when you have really few demands on you other than to learn, which is a really nice thing. As a graduate student or as an undergraduate, it may feel pressured and intense, but as an old guy, I look back upon that thinking, boy, this was really fun. This was a great period in my life. All I had to do was learn stuff. At the PhD level, again, we expect people to be able to think, to code, to collaborate. We'd like to think that people come with a little bit more domain experience, with a little bit more expertise in one of these many areas. And on the way out, after you spend 3 or 5 years with us, we would expect you to have deep domain experience in at least one area, as well as being broad. So we hope that you can go deep in one place, but be broad in many places, that you've gone to a bunch of conferences, that you've written some papers. As a PhD student, you have much more autonomy to define a problem and carry out the research that fits within the overall project. And that's another great thing as a graduate student, that that is incredibly valuable, because that's the type of thing that you take away. The ability to do that and to think and to carry something to completion is a skill that is really helpful for the rest of your life. And typically it takes 3 to 5 years to get a PhD. So let me give you a sense, the other things that I thought might be interesting for you, whether they are or not, I don't know. Most graduate students, and I was certainly one of those, come to graduate school with a strong interest in one particular area. They come and they say, I'm going to work in quantum optics, whatever that is, right? And that's a good thing. It's good to have an idea of what you want to work on. But in your first year or two, it's also really good to be open to other areas, right? You're coming to graduate school, generally you're not, in some cases you're older and maybe you have a ton of experience, but very often you're younger and you may think you know what you're interested in, but you haven't been exposed to the whole plethora of things. And so that exposure and being open to that is really important as well. Or maybe, lots of times, life gets in your way a little bit. You might really want to work in quantum optics, but funding isn't available to work in quantum optics. So at the University of Colorado, certainly you have the ability to be a TA, but even better than being a TA, a teaching assistant, is to be funded out of a research project, because that makes things go faster for you, gives you more time to really work on it. So funding is important. Or there's funding available, but you don't like the group, or you don't like the professor. And so being open to other things and being able to pivot is a really important skill. It's like starting a startup company where, you have a startup company and you think you're going to go this way, but something happens in the middle and you have to take what you're doing and pivot a little bit in another direction. It's the same thing for being a graduate student. Another thing is not to become a professional graduate student. You're certainly your PhD or even your master's work is not going to be your most important work. It's probably the first really important thing that you've done, or one of the first really important things that you've done. And so sometimes students have a tendency to think, I have to do something so well that it's brilliant, okay, where it's not really what you have to do. What you have to do is solve the problem and don't get stuck, but to keep going. So it's your job as a graduate student And it's also your advisor's job to make sure that you can make a contribution, that you can solve a problem, but at the same time, making sure you get out in a reasonable amount of time so that you can take that expertise and live a long and fruitful life and continue to make contributions. Listening to students is your fellow students is really important. I always found it invaluable. It's like my daughter is in the medical profession. So I wanted to know, should I go to this doctor or this doctor? And she knew both of them. And she said, you don't want to go to that guy because, he doesn't know what he's doing and he screws up his patients. You want to go to this woman. I work with her all the time. We're colleagues and she is terrific. Your students know what are the interesting courses, who are the good professors, keep talking to them. And then the last thing that I want to leave you with is I often see that sometimes students get stuck. You're not going to go for a PhD without being somebody who has a lot of gumption, a lot of ability to stick with it because it takes a long time and you want to figure it out yourself. And that's really a good thing, right? But sometimes people get blocked. It doesn't stick, but you wrestle with something for months. And that's not the way the world should work. That's why having colleagues all over the world and peers is really important, right? If you get stuck, go ask somebody. Talk to your fellow graduate students, talk to your friends, go and talk to your professor. Don't give up too early, but don't give up too late and let yourself get blocked. So I think I've used up all my time. I'm sure I have. I'm willing to answer as many questions as you want. How do I pronounce your name? PS? PS?
KCA, it's a Ghanaian name. I'm from Ghana. So yeah.
Where are you from?
I'm from Ghana, West Africa.
Cool. I have a really good colleague from there. Okay, go ahead. What's your
Oh,
question?
okay. So I wanted to ask if you taking students from other engineering department, like maybe electrical engineering, um, in your lab.
Yes. Yes, we do. In fact,
Okay.
one of my current students is from electrical engineering. And absolutely.
Okay. All right. Thank you.
Any other questions? Have I bored you guys completely? Did I waste an hour
No,
of your
no,
time?
not at all. Not at all.
No, not at all.
Good. Well, I don't mean to make you stay the whole time. I think I think so. So I think I'm here, and I'm also I'm also in the on the web. Feel free to send an email or drop us a question or talk to any of our current students. And I appreciate your time.
Thank you so much. Thank you so much.
Okay, you're very welcome.
Thank you so much, sir.
You're very welcome, guys and ladies. Have a good day. Take care. Bye-bye.
Bye.
There's one person in the chat. What do I say? Oh, thank you. Okay, that's great. Okay, thank you so much. Now I have to turn off the stop sharing, stop recording.